All right. So we're going to talk more about summary statistics today. We're going to expand our conversation to measures of spread. We're going to keep talking about graphing. So we're interested in populations and we're interested in samples. And just as a review, we're inherently interested in population level parameters, but we can almost never measure them directly. So instead, we estimate these population parameters by taking samples and calculating statistics. So we use Greek letters to denote population parameters and Roman letters to denote sample statistics. For example, when you learned about calculating the population mean, you would represent that with mu, but when you learned to calculate the sample mean, you would represent that with a y bar. Now, when we move into spread, we're going to use some new Greek and Roman letters. So for example, to calculate the population variance, we're going to use what's called the sigma squared, and it's a lowercase sigma. So just like there are lowercase and capital Roman letters, there are lowercase and capital Greek letters. So just to confuse you, because we've already used the uppercase sigma, the population variance has historically been represented by using lowercase sigma squared. And the sample variance, it's a little bit easier, is represented by using s squared. Now, we just take the square root of those two values to get what's called the population standard deviation, sigma, and the sample standard deviation, s. And I'm going to talk you through how to calculate all of these things. So measures of central tendency, this is just a brief review from last week. Remember, we can calculate the mean as an average value. We can calculate the median as the middle value of a data set. And we can calculate the mode as the most frequent value in a data set. Okay, so we're going to move now into measures of spread. Okay, so we have the center of each value of each data set, the central tendency of it, but how far out, how much spread is there around that center value? That's what we're interested in next, because it's an important part of what we're learning about is how to characterize a data set. So the first thing, it looks kind of ugly, but we're going to walk through it. So sample variance, again, we can't measure population variance. So we're going to start with sample variance. We take a sample, and we're going to calculate this value called s squared. Now, I'm going to start with what's in the parentheses because that's typically an easy place to start. So again, we're talking about a data set, a set of data points, y sub I. So there could be 5 y's in your data set. There could be 500 y's in your data set. Okay, so y sub I is a placeholder for each value in your data set, numbered from 1 to n. Okay, and y bar you learned about, that's the sample mean. So what you're basically doing with sample variance is you're saying each data point in my data set, I'm going to subtract the mean from it to see how deviant is each value from the center, right? How far away is it from the center, which is the mean? And because some of those values are going to be bigger than the mean and some are going to be smaller than the mean, just like other statistics, we're going to have to take that difference value and square it to turn them all into positive numbers. So all you're doing is taking each data point in the data set, subtracting out the mean, the sample mean, and squaring it. And then you're going to add up all those deviations. Okay, so now that's where the sigma comes in. So the sum from I equals 1 to n of every value subtracted from the grand mean squared. Now you're going to add those all up and you're going to get this big number, right? And so basically what you need to do is divide that. It's not exactly like the mean. You're going to divide it by n minus 1. Okay, so you're basically dividing by degrees of freedom. And that kind of just helps to bring the number back down. to give you a sense of the sample variance. Now, keep your eye on that equation because when I move to the next measure of spread, which is the sample standard deviation or S, it is literally just the square root of that whole thing. Okay, so keep that in mind because although it looks messy, we've already gone through this one. So S, the sample standard deviation, is the square root of S squared. Okay, that makes sense. And it's just the square root of that big ugly thing. Okay, so the sample standard deviation is another measure of the variability of all of the measurements around the mean. It's a very commonly used measure of spread. It's a smaller number than the sample variance. Okay. And then the last one that we're going to talk about is you just take S, the sample standard deviation, and now this time you divide it again by the square root of n. And this is called the standard error of the mean, or S sub y. Often it's just abbreviated SE. So the SE is equal to the standard deviation divided by the square root of n. And this is really commonly used. It's a smaller value than standard deviation, so it makes graphs look tidier when you put error bars on top of bar graphs. But it's really trying to get at something slightly different. It's a measurement of the variability of the estimate of the mean itself. Okay, and it's commonly reported on graphs. So these are three different measures of spread, kind of like there were three different measures of central tendency, just different ways to talk about how much variation is there in a data set around that center value. And I'm just going to talk because those three values are typically used with the mean. But if you're reporting the median as your center value, then you should instead use either the range or the quantiles. And so the range is really simple. It's just the lowest value in your data set to the highest value in your data set. That's the range. And just like the median is the middle number when you order things all along, you would want to order your whole data set and then you'd take chunks of the data set basically to determine the quantiles. And quantiles can be any percentage of the data, but usually you report the 25th quantile, the 50th quantile, which is the median, and the 70th quantile. And those would be called quartiles because they're 4 quarters of the data. And so a box and whisker plot is used more commonly to show, and here you can see the median, and then the box is made up of the 25 and 75% quartiles. And then you have the range showing the lowest value and the upper value in a box plot. So again, getting back to these graphs, now this makes a little bit more sense, right? Now I'm showing you a bar graph where the bar is the mean. In this case, the error bars are the standard error, okay? And when the error bars overlap, that means there's probably not a difference between the two bars, even though they don't look exactly the same. Because there's so much overlap in the data set, it's unlikely that there's a significant difference between these two streams in terms of species diversity. Now, here's a different one where the error bars are again the standard error and the bars are the means. But now you can see there's likely a significant difference. We're going to get into these kinds of tests soon, but I just want you to focus on the graph. So note that there are axis labels on the graph. We're going to try to figure out how to do that in Excel because the default in Excel has no labels, which is not very smart. And this would be how you would graph a continuous Y with a categorical X. Okay, the last things I have are 2 statistics jokes. I'm sorry that there's not a class around to laugh at my really bad statistics jokes, but now that you know something about standard error bars and standard deviation bars, maybe you'll understand why they just can't trust bar B. Oh, poor bar B. Or you could look at this one, which isn't really a joke, but it's just a really cute image that's asking, are your summary statistics hiding something interesting? What's interesting about this is that when you graph just the mean and the error bar, you're kind of ignoring the the real variation in the data. So there's kind of a movement to graph the actual data points alongside the mean and the error bars. So this is just something kind of fun. All right, see you in the next lecture.